Hi, I've just received a request to publish a basic understanding of fluid dynamics at KS5 post 16, and I'd just like to give you a 3-page basic understanding of fluid dynamics as it stands for A-level and BTEC students. Fluid dynamics investigates the movement of solids through fluids, and it also investigates the movement of fluids through solid infrastructure. And so in the first case, it's the movement of solids, ball bearings, components, equipment in fluid media, whereas in the second case, it's the investigation of water or fluid or oil through pipes. And although I'm not going to go into area and velocity equivalence, that's slightly but I will try my best to explain the philosophical understanding of viscosity and how it's related to the mathematics and how is it calculated. As you're able to see, viscosity is understood or taken as a measure of the average thickness of a fluid. That's the way I'm trying to explain it. So it's a measure of the average thickness of the fluid, viscosity, and in the books it's mentioned as the quantized estimate ratio of the internal drag of the fluid. Now, it's not a ratio in its own right. It's viscosity. So just like we have momentum, where the units are Newton seconds, the units for viscosity are Pascal seconds. So it's not pressure transmission per unit time, but it's pressure momentum. It's you could understand it as similarly to Newton seconds, it's pressure seconds, and Pascal seconds. So newtons per meter squared, and then seconds. So it's pressure seconds. So it's it's a bit like impulse, FT, Newton seconds, and it's the impulse in terms of pressure. So viscosity is highly dependent on the formula of the relationship of drag, and in its without going into details, mu or n, as it's represented as curved n in Greek, it's basically a ratio of the stress to velocity divided by distance, and it comes out as Pascal seconds, and it's newtons per meter squared seconds. So it's basically pressure seconds, and the formula is mu equals stress over delta V, velocity, so it's stress times distance over velocity, which turns out to be force over area divided by velocity divided by whole divided by length, and so it comes out to be pressure seconds. And this is, as I said earlier, sort of an impulse in terms of in with respect to fluid movement, fluid transmission. So it's more of a pressure evaluation as it goes along from point A to point B, and it's heavily dependent on drag, which is the product of the density of the fluid, velocity of the fluid, and the area, the cross-section area of the fluid, which is usually the area of the pipe. So so viscosity and drag are interlinked, and the units for drag is force, and the units for viscosity is pressure seconds, newtons per meter squared, and then seconds. And viscosity is to do with flow, so it's interlinked to the idea of flow. It's not, remember, we are talking about fluid dynamics, not fluid statics. So flow, wherever there's flow, i.e. fluid travel from point A to point B, fluid dynamics and viscosity and drag will come into play. And flow, I refer it to the interaction of vehicle and atmosphere. So the vehicle could be a ball bearing being dipped in a jar of glycerine, or a measuring cylinder of honey, and or glycerine, or any other thick oil or oil, motor oil. And it has two types of flow, i.e. the first one is turbulent, which is more real life, and then you've got the idealistic laminar flow. So the laminar flow is idealistic and often desired, and that's what it's the dream of every manufacturer to produce vehicles that have the least amount of drag, highest amount of fuel efficiency, and they're trying to marry the two together. And it's the lexicographic opposite of turbulence, referring to a smooth, fuel-efficient interaction between the vehicle, i.e. a ball bearing or a car or a double-decker, and the environment. So lower the drag, higher the fuel efficiency, and if higher the drag and higher lower fuel efficiency would mean more turbulence. And so a vehicle is set to experience turbulent flow, either in an aeroplane or a car, when the drag outweighs the fuel efficiency. It begins to overpower and burden the fuel efficiency beyond its transmission means of transmission, and it begins to reduce the effective power output, leading to an increase in the deceleration ratio. So it would be quicker for the vehicle to come to a stop because it's the velocity is coming down at a far faster rate, or it's having to expend more energy to stay at the same velocity. So this is what these are the founding principles of the branch of physics called fluid dynamics, and I hope you learned something today. If you have any questions, please do post them down below in the comment section. I'll try my best to answer it. And if you have any comments pertaining to me trying to solve fluid dynamics questions, then please don't hesitate to get in touch with me. Thank you very much. Take care. Bye now.